So, hello everyone, welcome back. Let's start problem number 5.15 on page number 240 of Griffiths electrodynamics. He says saying that a thick slab we need to consider and carrying volume current as J, and we need to find out magnetic field both inside and outside. So, it is like a rectangular slab, and he's saying that we need to calculate magnetic field here and here. So, we'll just simply apply the imperial circular law, that imperial loop. According to uh, we need to consider a closed loop so that we can calculate B, because otherwise magnetic field will be zero if we are not according to this equation, if we are not considering the any closed loop. So from the equation we can see that if this is X and this is Y, this is Z. So he's saying that X, we have uh, current in X direction, and Y and Z are infinitely uh, infinitely long. So this is, sorry, Y and X are infinitely long, because and Z has some dimensions. This is minus A, this is A plus A. Oh, sorry. Let's. This is not minus A. This is not plus A. Let's make the figure again. So the figure is something like this. If I'll replace this Z by this. This is X, this is Z, and this is Y. So these coordinates are minus A and plus A, and here in this direction the uh, current is going on. So J is given. So simply if we integrate, uh, we will know that di by dA is J, volume current density, and A is the area. So I enclosed can be given by J into A, where A is the area. So on putting the following, so first of all we need to consider closed loop. So closed loop can be this can be a closed loop which can be extended from minus A to plus A. All right. Or this can be, I'm sorry, this can be a closed loop, because the limits of Z, the limits of Z can will not make a sense if I place. So this can be a closed loop, because the limits minus A to plus A will make sense here. So if we consider this closed loop, and we'll consider a current going from this closed loop from here to here, so magnetic field, the direction of magnetic field is uh, uh, if we place our fingers in the direction of current and curl them in the direction of where, and curl them from where the we need to take uh, the distance. So just a second. Yeah. If we curl them, so X cross Z, so it is minus Y, because this is the direction of current. uh, I cross DL, this is the correct direction of current, and in which direction we are curling our fingers in this direction. So if we place here, if we curl, then we'll get magnetic field over minus Y cap. So we have decided our direction, so it is B dot L and mu naught. What is I enclose J dot A, and J dot A can be written as J into L into some Z with minus Y cap direction. All right. So B is equal to mu naught J Z with minus Y cap, and this obviously is the direction of magnetic field when Z is between minus A to plus A. But when we go inside the uh, circular slab, or sorry, rectangular slab or thick slab, it becomes minus A if Z is greater than A. All right. And if Z is less than A, it becomes plus A. Or if Z is greater than minus A, if Z is greater than minus A, it becomes plus A, because we have considered the circular loop like this. And if it goes downside, then we will get plus a because of minus a because of the direction opposite, and if we are going above towards z, positive z, then we'll get minus. So this is the solution for this video. I hope you understood. We need to consider spherical loop. Just a second. Empirical loop, not spherical loop, sorry. Empirical loop, and put the values just simply. This is the solution. Thank you. See you in next video. Bye bye.